This for phase 1A of TI analog design vendors. We have implemented second order low pass filter using the ASLK starter kit. So here is our circuit which we have implemented on this kit, and the transfer function we have calculated. It is given by this expression. As we can see that in the denominator we are having a quadratic equation in omega square. So as a quadratic equation has a minima, and at that minima this magnitude response will have its maximum value, and that omega can be calculated by minus b by 2a, and it is coming out to be gv by root 211. And after this omega, the magnitude response starts to increase. The denominator starts increasing, and the magnitude response starts to decrease. And similarly, when the magnitude response will come out to be 1 by root 2 times of its maximum value, that will be the 3 dB cutoff, and the 3 dB cutoff is coming out to be under root of root 5 plus 1 upon root 211 into GB. Now this op-amp will be having a slew rate, and from the IC we can see that the minimum slew rate is 8 volt per microsecond. So we have selected a sine wave of magnitude of 25 millivolt from peak to peak, and the maximum frequency till which we are going is 1 megahertz. So the maximum rate of change of voltage will be 25 divided by 2 into frequency, maximum frequency, that is 1 megahertz, and it is coming out to be 0.05 volt per microsecond. So 0.05 volt per microsecond is much less than 8 volt per microsecond, so it is reasonable. So we have applied a sine wave of magnitude of 25 millivolt peak to peak, and we have started from few kilohertz, and we will go up to 1 megahertz. This is our circuit. Now in the low frequency, we can see that the output, which is in channel 2, exactly matches the input both in magnitude, and the phase difference is 0. Now I am increasing the frequency, and the gain is still 1, but we can see that we can see the phase difference. Now further increasing the frequency, and now we can see that the output has increased. The gain is more than 0 dB, and this will occur up to a fixed point, because we have seen that the denominator is a quadratic equation. So it will, as the denominator is a quadratic equation, the gain will increase to a fixed point, and then it will start to decrease. Now we see that gain is still increasing, and up till this approximately 180 kilohertz, it has reached its maximum value, and now it has started to decrease. Now gain, which is on channel 2, has started to decrease, and a fixed point up till which it has reached 1 by root 2 times of its maximum value is the 3 dB bandwidth, and it is coming out approximately at 275 kilohertz, where the gain has reached 1 by root 2 times of its maximum value. The output has reached 1 by root 2 times. The output has reached 1 by root 2 times of its maximum value. Now we can see at this point the phase difference is coming out to be sine inverse of 5 by root 2, which 5 by 12, sine inverse 5 by 12, which can be calculated by sine inverse of y by y minus. Now to study the transient response of the circuit, we have applied a square wave of peak value 1 volt and frequency 100 hertz at the input, and we are studying the output. As you can see that the output first shoots up, and then after sufficient time it reaches its steady state value. and we have calculated from this from the reading on the CRO that the rise time is coming out to be 8 microseconds and the overshoot is 0.08 millivolt.